Welcome back to the COS 217 lecture. This is the second in a series of lectures that, when put together, make up a sort of crash course in the C language. In the first lecture, we saw variable declarations and assignment, C control flow structures, and a brief tour of the interface of C's standard I/O library. In this lecture, we're going to look at numeric types provided in C, their operations, and their internal representation. Let's start with whole numbers. Diving right into it, here are the types provided in C89. There are two variants of each of char, short, int, and long. Chars are 1 byte, the others are not specified exactly, but instead relative to each other. Ints are seen as the default, and are typically, but not necessarily, matched to the machine's natural word size, corresponding to the register size or other architectural constants. Java made a different design decision. It explicitly specified all of the sizes. For one, there was no concept of a natural word size because the underlying hardware doesn't matter to Java. We're always working in the environment of the JVM. Additionally, Java changed from char as the base type with 1 byte to byte as the base type with 1 byte, with char actually being 2 bytes. So by not setting absolute sizes, C forgoes portability, which seems actually a reasonable choice considering that C was written as a systems programming language. But it also seems that there would have been very little cost to supporting both systems and application programming, with a greater variety of types. For example, we could provide types that self-specify their size, something like int 8, int 16, int 32, int 64, and then also the system-dependent int. Java also, I think, gets it right with byte instead of char for two reasons. Number one, bytes aren't necessarily characters. They might just be small ints. And number two, characters aren't necessarily 1 byte entities, as we'll see soon. But now that we have the types defined in the language, we need to know how to indicate literal values for them in code. A numeric literal that looks like an integer implicitly has type int. And as seen in the last lecture, we can specify an int literal in another base by putting a prefix to it, 0 for octal or 0x for hex. Careful though, because the 0 prefix for octal is prone to confusion, simply because it breaks our sense of mathematics with leading zeros being superfluous. Some other languages chose to do 0 lowercase o for octal prefix, and I think this is a little bit less confusing, but that said, plenty of languages do follow with C with just a 0. So continuing to analyze with the benefit of the passage of time and experience seeing what industrial code in the language does and doesn't do, it seems like it would have been logical to use an S suffix to indicate a short literal, and it's curious that the designers decided against this notation or any notation at all. It's not clear why they made that choice. The same for the lack of a suffix for a bite-sized literal, although there it could be because they're thinking of these as characters, and so there are other ways to specify character literals that we'll see later. But in case you think I'm bagging on C, I'll note that Java inherited both of these eccentricities. So either it's the case that even newer languages fail to correct these perceived faults in older languages, or maybe they weren't such faults at all, and we should just live with them even if they're not perfectly parallel or perfectly consistent. Alright, before you tune out, let's go to something completely unlike anything in Java. We can specify that a type represents only non-negative integers. This is a design choice that I think made sense because of the differences between the two languages. C is an older language, and thus its design assumes more memory constraints than the younger Java. In Java, where an int stores negative 2 billion approximately to positive 2 billion, if you want to hold 3 billion, the simple answer is, well, then use a long. In C, the designers let you double the maximum value of any given type by shifting its range from approximately negative x through x to 0 through 2x. C is a lower level language also, which deals with quite a bit of bit whacking. For example, bit masking, where we use the values of each bit in an integer as separate flags, and thus we have to isolate them via bitwise operations. When we treat these values as bit strings rather than actual integers, it doesn't make much sense to think about the integer value as signed. And thus it's convenient to have a type that doesn't have sign information built into this representation at all. The literals here are like the signed types we saw before, including limitations of having to cast to short, but with U indicating their unsigned nature. So last, before we move on to representation, is the char data type. Chars are in this section of integer data types because that's really what they are. They're just really small ints. Even though their name betrays that their designed intent was for working with ASCII characters, they're just 8-bit ints. As discussed, perhaps they should have been called byte or int8 or something similar. In particular, the naming becomes tricky now that we know about signedness. The concept of a signed char is tough to wrap your head around. What exactly is -a? For actual ASCII characters, the difference between signed and unsigned values doesn't really matter. The highest ASCII character is 127, so either signed or unsigned will be fine. If you want a 1-byte type for a calculation, though, you might, maybe even should, use an unsigned char, though. Because as much as -a doesn't make sense, the positive or negative nature of arbitrary data makes even less sense. An example of using chars for arbitrary data would be for a base 64 conversion, which is an algorithm that has to account for not just ASCII but arbitrary data and uses the entirety of the 8 bits in a byte, not just the 7 bits used by ASCII from 0 to 127. Although we're continuing to think about chars as really small ints, the language designers did provide literal values that indicate their common usage as text characters. I'll take this opportunity to point out something for assignment 1. Each of these values is 1 byte. Yes, some of them have multiple characters inside the single quotes, but those are just how we represent the literal. Consider \n. If we wanted to type a literal new line as hitting enter or return, our code would be a mess. Open quote, return, close quote. Ick. Instead, the language designers gave us a way to identify this character, uniquely using the backslash as an escape character. An escape indicator says the next character isn't necessarily what you think it is. And since each character literal refers to a single character, there's no ambiguity here, versus the character backslash and then the character n. Similarly, to represent a quote character, we have to do something special. Because we can't use 3 single quotes, the second would close the first, and then the third would be opening some new quote that wouldn't ever end. Instead, we use the backslash to say the next character doesn't mean what you think it does, so the second quote in the sequence doesn't close the character literal, and thus the third one does. Taking it one step further, the character literal for a backslash then needs to have a backslash to escape the backslash character, which would otherwise be interpreted as escaping the closing quote. Whew, that got a bit meta. Alright, so another important point brought about by these examples is that there's a big difference between the character literal 1 and the integer value 1. The character literal 1 is a way to indicate the char with ASCII value 49, which is the ASCII value of the character 1. This is different from the integer 1, which corresponds to a non-printing character with ASCII value 1. Similarly, the character literal 0 is ASCII value 48, which is not 0. The value 0, aka the null byte, is represented by the character literal with the escape character \0. One more note. Oddly, char literals are really of type int. We never think of them as such, but in reality, under the hood, they're ints. Not just they are an integer type, but they are ints. So C gets tick a tick works only because C supports automatic demotion. That's a weird choice. You would think that literals that are pretty explicitly tied towards chars would be chars, but they're not. They're ints. That said, when you consider that we have seen that you can do arithmetic on characters, there had to be a choice. The language designers chose to have implicit demotion on assignment instead of implicit promotion with arithmetic. This doesn't really impact us as programmers in any way, as far as I can tell at least, but it is an interesting design quirk that to me at least speaks to the appreciation we have to have for language designers in making decisions in situations where there's no obvious right answer. Alright, so those of you with diacritics in your name are already painfully aware of this, but ASCII is a rather limited set of characters. Unicode has the expressive power for far more characters. How many, you might ask? Well, whenever I need an answer to a question, I ask Randall Munroe. Unicode has 140,000 characters defined and the capacity for more than 1,000,000. Standard ASCII characters use 1 byte. Most Latin-based alphabets use 2 bytes. Chinese, Japanese, Korean characters use 3 bytes. And some historic scripts, mathematical symbols, and yes, emojis use 4 bytes. So Java might criticize C for having too small a char with its 1 byte char, but as it ends up, so does Java with its 2 byte char. In fact, so would any language with a character size set by the language. This comes back to this idea about language design. We should build languages with fundamental types in computing, and perhaps those will be adapted in different ways to different applications. If we design for applications, we're doomed to fail as applications evolve. But now, since we can't change the size of a char in C, how does C implement variable length encodings like Unicode? It's not in the language itself, instead it's in libraries. And in this case, most of the libraries use byte strings. Alright, so these are all of the integer types in C. Here's a handy summary slide. And now, having seen all of them, we get to talk about how they're represented under the hood. We'll start with unsigned integers because they're actually easier than signed ones. The natural numbers range is, of course, unbounded. But in the finite universe, and in particular finite digital computers, we don't really play well with infinity. So any given integer's type range, any given integer type's range, is constrained by the number of bits in its representation. For our computers at 32 or 64 bits, this is far too large to get really a sense of the processes involved, so let's imagine a dinky little computer for that purpose. We'll use a 4-bit machine, figure out the right characteristics and algorithms, and since we can wrap our minds around that 16 possible values, and then hope, and in fact it will, generalize to larger machines like ARMLab. So let's start out on our 4-bit computer. We'll try to assign each of the 16 values a unique representation in those 4 bits. Start at 0, well, for 0 we could use all zeros. Next comes 1, might as well start with 0001. This looks familiar. Oh right, it's just 4-bit binary. Great, we know all about this. So now let's see how it shakes out for the operations we want to do on these integers. If we're just using binary as our representation, then binary arithmetic is how we'll do addition. Simple, right? 3 plus 10 is 13. In binary, we can add using the exact same right to left carrying algorithm that we know from elementary school in decimal. But there's a problem. What happens when we exceed the maximum value we can store in 4 bits? It's overflow. In math, we can carry arbitrarily to the left, but here we have a limited set of columns. Overflow is when we're carrying and run out of columns. The result is that we wrap back around, starting at 0. The effect here is that all results are mod 2 to the 4, because we have 4 bits. This means that if we do our addition without considering the number of bits, but then afterwards take mod 16, we'll see the result. The example here is 7 plus 10 is 17. We mod that by 16 and get 1. So pause the video for a second and think, how would you detect overflow programmatically? If the sum is less than 1 or both of the add-ins, then there's overflow. We can't add 2 unsigned numbers and get a smaller number without there being overflow. So subtraction in binary is again just like you learned subtraction in elementary school. Right to left, borrow is necessary. How would you detect overflow programmatically? The intuition here is that we want something that would result in a negative, which we can't do in unsigned land. And so that is, if the first operand is less than the second operand, that will result in overflow. The last operators that we want to look at for unsigned integers are the bitwise operations. Let's start off with shifts. This just moves every bit down in the specified direction. So 10, 1010, right shifted 1 bit. We move the 0 in the 1's place right, where it falls off the end of the number and disappears. Then the 1 in the 2's place fills into the 1's place. The 0 in the 4's place fills into the 2's place, the 1 in the 8's place fills into the 4's place, and that leaves nothing in the 8's place, so we just fill in with 0. If we right shifted by 2, we'd do the same process again. So starting from the result there, 0, 1, 0, 1, the 1 in the 1's place goes away, the 0 in the 2's place ends up in the 1's, the 1 in the 4's ends up in the 2's, the 0 in the 8's ends up in the 4's, and we fill in again with 0. 0, 0, 1, 0. Left shifting works the same way, except that it's moving left from the 8's place, so we fall into the great bit chasm in the numeric ether that direction instead. And when we reach the rightmost bit that has been vacated, we have to fill in with 0 on that side. So now pause the slide, make sure that you get the algorithm to reproduce these calculations, and think about what are the arithmetic effects of each. So what are our answers? This isn't magic. You've known this since elementary school, in fact, just regular decimal counting. What happens when you remove the last n digits? Well, you're dividing by powers of 10. For example, 12, when we remove the last digit, we get 1, and that's integer division by 10. The same thing here. Right shifting by n bits is division by 2 to the n. And for left shifting, the same logic goes. Adding zeros to the right side of a number in decimal is multiplying by the base, multiplying by 10 each time. So adding n zeros to the right side is multiplying by 2 to the n. Note though that in elementary school you never had to deal with overflow, which we do in this case. Here's one last example for that. When we start with the 1100 from 3 left shifted by 2, and we left shift one more, the 1 falls off the left side. That's overflow. But like with addition, if we do the calculation without overflow, then mod by 16, we get the appropriate answer. 11000 is 24, mod 16 is 8. Alright, that was the longest of the bitwise operations. Let's run through the remaining 4 quickly. Bitwise not, that is bit inversion, literally just flips every bit. But warning, remember we have to flip the leading zeros too. It's easy to remember this in 4-bit arithmetic, but it's sometimes hard to remember in 64-bit arithmetic. This is probably the most common mistake on the midterm or the final exam questions on this topic. So bitwise AND looks at each column in isolation. And for each pair of bit values, it computes the AND between them, where 1 is true and 0 is false. So 2 1s make a 1, anything else makes a 0. The examples here show some common usages. AND with 1 less than a power of 2 masks out the higher order bits to 0, leaving only the suffix of the bits. And with the kth power of 2 isolates the kth bit, leaving it alone while making all the other bits 0. Bitwise OR again looks at each column in isolation, and for each pair of bits, this time computes the OR between them. Thus 0 or 0 makes 0, anything else makes a 1. In the example, we have the sort of opposite of the power of 2 with AND. This turns the kth bit on to 1, leaving everything else unaffected. And finally, bitwise exclusive OR, where for each bit, if they're the same, it produces a 0, and if they're different, it produces a 1. This has several usage. XOR with 1 flips the value. XOR with the self, with itself sets a value to 0. And we'll see that reasonably often in assembly language. We could also do XOR with 0 to keep the value the same, but this is somewhat unusual, except maybe for individual bits in a bit mask. And even then, we normally use AND with 1 instead of XOR 0. Alright, so here's a sort of tricky problem using bitwise operations. Please pause the video, take the time to actually figure this one out, and when you're ready, start again. Alright, so A here, 0 left shifted by k times is still 0, so ending u with it still gets 0. Shifting 1 left k times gives m, which is the total number of bits, n minus k zeros, and then a 1, and then the rest of the k zeros. So when you OR that, it makes the kth bit 1 and keeps all the other bits the same. But we didn't want the kth bit to be 1, we wanted it to be 0. C, we're going to left shift by 1 by k. That gives, again, a whole bunch of zeros, a 1 and a 0. We knot that. That gives a whole bunch of 1s, a 0 and a 1. When we OR that, it makes the nth bit whatever it already was. ORing by 0 doesn't change anything. And further, it will change other bits if they were zeros, since they're getting ORed with a 1. But we're really close here. So in fact, D is the right answer. When we left shift by k, 1 by k, it gives a whole bunch of zeros, 1, zeros. Knotting that gives a whole bunch of 1s, 0, 1s. ANDing makes the nth bit 0, because x, for whatever value of x is, ANDed with 0 is 0, and it keeps all the other bits the same, because anything ANDed with 1 is itself. So we can use these operations to do some arithmetic parlor tricks, if you will. Code can use them, however, to improve speed, because bitwise operations are fast, and multiplication and especially division are slow. That being said, faster is not always better. This sacrifices a lot in terms of code readability, but luckily compilers also know these silly parlor tricks, so we won't have to write them in a high-level language typically. But you should be aware of them, because it can save you an hour of your life trying to figure out what the heck the compiler-generated assembly code is doing. Alright, so everything was going well, but now I have to remind you, unfortunately, that negative numbers are a thing. So signed integer types will have to represent them. Since we are working with bits now, can't we just make a bit a negative sign? Actually, can we? Maybe we can make a bit represent a negative sign. In sign magnitude representation, the leftmost bit is now the sign bit, and 1 is effectively a negative sign. Things look good so far, looking at this just at a glance. It even has this nice property where computing the negative is trivial. Just flip the higher order bit. Except, wait a second, I didn't know this before. What the heck is negative 0? And if there are 2 zeros, that's going to be a problem for our standard math operations that we saw with unsigned ints. Consider, negative 5 plus 5 is, well, 0, 0, 1, 0 is 2. So that's neither of the zeros. And negative 0 plus 1 is negative 1. Yeah, this will be requiring entirely different algorithms. There's got to be a better way. So instead of using the leftmost bit just as a negative sign, what about if we made a negative transform every bit? 1's complement negation is just flipping every single bit. So if 5 is 0, 1, 0, 1, negative 5 is 1, 0, 1, 0. This still has really easy negation, just flip all the bits. It has a little bit better time with simple operations. Negative 7 plus 6 is 1, 1, 1, 0, which is negative 1. That's great. Negative 5 plus 5 is 1, 1, 1, 1, which is a 0 value. It's negative zeros. That's not great, because that means we still have negative zeros, but it works. Alas, though, all addition isn't fixed. Overflow can be a problem. Consider negative 4 plus 6. 1, 0, 1, 1 plus 0, 1, 1, 0 gets 0, 0, 0, 1, which is 1, not 2. So we can still hope for something better. That last one had promise, though. If we could eliminate the double zero, we'd be in business. And we can eliminate the double zero by having one more negative or one more positive number than the opposite. Once we do that, the addition problem should go away also. To solve this, we're going to use overflow as our friend rather than our enemy. We take the idea of negating all the bits from 1's complement, but to rid ourselves of the concern about 2 zeros, we add a 1 after negating all the bits. This means that 0, 0, 0, 0 flips to 1, 1, 1, 1, and then adding 1 gets you back to 0, 0, 0, 0. Even better, this is a function that's symmetric and self-reversing. So consider 5 and negative 5. 0, 1, 0, 1 becomes 1011, that's -5, great. And 1011 becomes 0101. That's 5, so it goes the other way. Awesome. The only quirk left here is our extra value 1000. What's its 2's complement? Well, we flip all the bits, 0111, add 1, back to 1000 itself. And since this is the one extra value that we got by taking away the -0, this makes sense. It also makes sense intellectually in terms of how we think about overflow as resetting from the highest to the lowest. With unsigned, that meant rolling back over to 0, but now it means rolling over from +7 to -8. Negative -8 would be +8, which overflows back to -8. This could work. In fact, 2's complement is not just a viable system. Almost all computers today use 2's complement to represent signed integers. It has nice properties and its pros, and the con listed here really isn't a con at all. It's a bonus number that still fits within the arithmetic and our intuitive idea of overflow. One big thing to note, though, is that we do have to know how many bits are in a number. Otherwise, we have no idea how many leading zeros have to be flipped when we flip all the bits and then add 1. This, again, is a common cause of incorrect answers on exams. Alright, so the other great thing here is that there's still the exact same algorithm for unsigned ints, which is our intuitive base 10 counting algorithm, except with a limited number of columns. In this case, though, the limited number of columns make the algorithm work, as in the positive plus negative and negative plus negative examples on this slide. It does, though, still pose the question of overflow. Pause the video and consider how you would detect overflow programmatically. So our answer here for how to detect overflow programmatically is if the signs of the add-ins are the same and the sign of the result is different. So if you add a positive and you get a negative, for example, that's overflow. For subtraction, it's similar. We have two options. We can perform our customary subtraction algorithm with borrowing, or we can transform the second operand to its 2's complement value and add. Since subtracting a positive is the same as adding a negative, and subtracting a negative is the same as adding a positive. So anyone can follow the algorithm of flip all the bits and add 1, or flip all the bits to the left of the rightmost one. But your analytic faculties might be tingling right now going, but why does it work? Well, first, we can prove that it does in fact work for each operation. The first algebraic derivation on the slide shows that negating a number and then 2's complementing the number are equivalent mod 2 to the 4, which is fundamental to the other derivations. And then the second one shows, for example, that subtracting signed ints works modulo 2 to the 4. We could do a similar derivation for each operation. It may not be apparent at first glance, but if we do a series of operations that will prove equivalent without overflowing, for example, x plus 3, then x plus 2, then x times 2, versus x times 2 and then x plus 10, they will also prove equivalent in the presence of overflow as well. And, like in the simpler case we saw before, the resulting values will, after overflow, be exactly what the values without overflow would be if modded by the 2 to the bits power. We could prove, again, this by derivations, like in the previous slide, or we can just rely on well-defined mathematical properties and not bother deriving, such as that modular arithmetic is a ring, and there's a nice property. Alright, so moving on, let's see how our bitwise operations go for signed integers. The left shift is identical, and indeed the arithmetic effect is the same, multiplication by 2 to the n. Again, we have to take into account overflow. Shifting -3 left by 2 should yield -12, but that overflows, and thus we're left with -12 mod 16 is +4. The right shift, however, is not so simple. Before, we filled in on the left with zeros. This continues to work just fine for non-negative numbers, but for negative numbers, it flips the sign. Additionally, because the numbers are counting backwards, that is, all ones is -1 and 1 with the rest zeros is the largest negative power of 2, The arithmetic effect isn't so obvious. An alternative would be to fill in on the left side with just the sign bit. This has the nice property of dividing by 2 to the n, just like with unsigned integers. In Java, there are in fact separate operators for these two algorithms. Greater, 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 the triple shift, shifts 0 into the leftmost position, while the double shift, just greater, greater, shifts into the leftmost bit, maintaining the sign. In C, though, the standard doesn't actually specify between these two options. Most machines, including ARMLab, implement arithmetic shifts. But because it's not the standard, it's a non-portable element of the language and thus should be avoided. Bitwise NOT, AND, OR, and XOR have no such complication. Their behavior is the same as for unsigned ints. The slide has best to avoid with signed integers, but I'd probably rephrase that actually and twist it around. If you want to do bit twiddling like this, you're almost always not using integers for their integer values themselves, and so you're going to want to make it an unsigned integer to start with. There's no sense in doing arithmetic operations as though it has a negative potential for a negative sign when you're really just looking at the bits in isolation or a combination of bits. Alright, so as noted before, Java doesn't support unsigned data types natively, which is probably reflective of a slightly higher level of abstraction, and you're not expected to be doing nearly as much bit twiddling in Java as programmers traditionally have done in C. So closing the book on signed versus unsigned types, it also has the nice benefit for Java of not having to worry about conversion between signed and unsigned integers, where converting a large unsigned integer effectively produces overflow, resulting in a negative integer. That said, I personally like C's inclusion of both signed and unsigned numbers, even with the complications that mixed type expressions have. It certainly fits C's freewheeling ethos, if nothing else. And if I had to quibble at all, I might have said that for mixed sign expressions, I might have required explicit casts, but that's a pretty nitpicky point to complain about. I think overall, even if Java has some nice reasons for why it doesn't have unsigned types, I've got to go with C on this one. So we'll finish our discussion of integer types with a few more language features relating to these. C's designers chose to add special purpose assignment operators to use a variable as an operand and then store back the result of the operation into that same variable. Java inherited this from C through C++, so this is all you've ever known, but even without that experiential bias, it does seem this was a good design decision. Number one, it's a very common algebraic idiom. The added feature is likely to be commonly used rather than rarely. One can perhaps quibble with some of the extensions, how often do you write shift and then equal, but once it's in the grammar for one numeric operator, the others come effectively for free, even if they get much less use. Number two, it's a win for conciseness. I++ is much more concise than I gets I+1. And it's a win for explicitness. I++ is most certainly an indication of what the programmer intends. I gets I+1, either of the variables I or the increment amount could in fact be a typo. I++, there's no ambiguity. That said, the existence of a pre- and post-increment and decrement is perhaps more confusing than it's worth, and it invites cryptic idioms where programmers will pack too many of the operations all into one line, relying on side effects from them, makes code difficult to read, even for experts, and utterly bewildering for novices. Speaking of which, let's see some of them. Again, pause the video, see if you can figure out what exactly this code results in having I and J after the third execution. So initially I gets 5, so I is 5, and J is an undetermined value. J gets I++, so I++ says I'm going to increment I, so I becomes 6, but then it emits the old value of I. So J is 5. Now J plus equal plus I, let's read from right to left, plus I increments I again, so I becomes 7, and emits the new value of I. So now J is plus equaling 7, so 5 plus 7 is 12. So j is 12 and I is 7. This was D. So again, take a minute. The answer's here. But take a minute and figure out why the answer is E. If you, when you traced, picked B, congratulations. You just got bit by the switch fall through that I guaranteed everyone would miss at least once. Hopefully this was your one time. But walking through this, inside the switch, we increment I to 2. But it's a post-increment operation, so it evaluates the old value. So we switch on the value 1, not the new value 2. But because we switched on the value 1, we execute case 1, we increment I, so it's now 3, and the pre-increment operation evaluates to I's new value. That's what's passed into the printf call, so we print 3. There's no break, so we fall through into case 2. Again, this is an easy thing to miss. It will bite you. If you got it here, still be on the lookout. So here we increment, so I is now 4, but it's a post-increment, so we evaluate to I's old value, and we pass 3 to printf. Thus we print 3, 3, I is now 4. The answer here is E. Similarly, almost the same problem. If you were to look at this even with fresh eyes, you probably wouldn't fail on the fall through again. But what about this weird conventional assignment combined with a special purpose assignment? Take a minute, look at it, see how you would have thought this would have worked if the answer weren't here. So this increments I to 2, and then the post increment evaluates to its old value. So the right-hand side of the assignment, we assign to be 1. Yep, we immediately overwrite the incremented value. Now we switch on 1, we enter case 1, we increment I. This is the pre-increment, so it looks at the new value, and so we pass a 2 to printf. We do the fall through again, but now it's the post-increment, and so we print 2, 2, and the correct answer is D. So as you've been working on assignment 1, you might have been getting frustrated with GCC 217 with all of its warnings and how strict it is. However, GCC 217 here does something super sensible. It correctly reports that the behavior of assigning a variable to an increment expression might be implementation dependent, or at least might not be what you really want to do. Unless you think that C is being unreasonable here, note that Java has the exact same behavior, and in Java's case, it's strictly defined that in the language specification that this is what should happen. But find bugs and spot bugs will point out such cases with a similar warning to what the GCC 217 compiler tuning has done. So in both cases, it's weird, but at least your compiler can save you. The last item for integer types actually applies to all types, but since the sizes of integer types aren't at all specified by the C standard beyond char, it's particularly relevant here. Within a program, we often want to know how much memory a variable requires. The typical case is for dynamic memory allocation, which we'll dive into in lectures 8 and precepts 8 and 9. Providing this feature allows us to write code that is a bit more portable than because we can parameterize our code by the local value rather than hard coding an assumed value in for the size of variables. So the sizeof operator, and yes, it looks like a function, but it's technically a compile time operator that takes an expression as an argument. That's kind of weird to take an expression. That can be variables, but it can also be types themselves. And sizeof it will return to us the number of bytes that an expression or a type or what have you will take in memory. So one last little tricky bit. What's the value of the sizeof expression for ARMLab? So here we promote the int I to a long because we're adding it to a long literal. And so we have a long and a long that results in a long. The size of a long, then, is 8. So even though the value is 3, size of the long is 8. All right, so the next variety of numeric type we should talk about is logical types. And I know you might be saying, wait, if it's a logical type, how is it a numeric type? Well, in C, there are no built-in Boolean types. Instead, we represent logical data using other types. When operators produce logical results, the specific values they emit are the int 0 for false and the int 1 for true. And when we want to represent logical values, typically we do the same, using ints or chars, where they will be interpreted with 0 as false and non-zero as true. This is fine, though not ideal. It's a bit confusing that, for example, both the char t and the char f are both true, since f's ASCII value is non-zero. And it's actually worse than that, because it's not just integer types. We could just as easily do something like pound define true to be 6.02e23, or pound define true to be 0 dot over 0 dot, because nan isn't 0 after all. It also means that there are some gotchas for programmers accustomed to languages with proper logical types, like Java, for example. So the lack of logical types means that common idioms from other languages, such as if I or if not I, are commonly applied here, but involve weird casting. It's not actually considered good in C because it's not beneficial to the computer. A reasonable compiler will generate the same code for either I or I not equal 0. And arguably it harms readability of code if someone is still tracking that I is an int. So it's sort of a dubious value, except to those already tuned to expect Boolean idioms. A larger problem, though, is the temptation to mix logical and numeric meanings within the same variables. Consider the second example here, where I ends up as the counter of the number of true clauses. It's weird, and also hard to read. People accustomed to Booleans will balk at the plus, and C programmers would have to consult a manual probably to check, wait, do relational operators return 1 and 0, or just some non-zero value in 0? Better not to risk either fate of misunderstanding or adding extra work to your code reader. Beyond allowing dubiously designed code, though, the paucity of types also makes the compiler's job harder. Consider this snippet. Imagine it's C code. What does it do? Now imagine it's Java code. What's the difference? The problem here is that the conditional should be I equal 5, not I gets 5. Since Java has a true logical data type, Boolean, that's distinct from integer data types, Java detects that if I gets 5, it emits an int and thus is erroneous. But C doesn't, and so C considers this to be perfectly valid. It's a true conditional because I gets 5 emits the 5, which is non-zero. So the effect here is that the value of I is changed to 5, probably unintended, and statement 1 is always executed, perhaps unintended. All right, so finally, because logical types are just int, we get weird overloading of logical versus bitwise operations that can cause confusion. If you apply logical AND to 2 and 1, then the result is 1. That's true, and true is true. But if you apply bitwise AND to 2 and 1, then the result is true and true is false, because 2 bitwise ANDed with 1 is 0. So and single and are quite different. There are other logical, and the same goes for other logical and bitwise pairs. Using one when you mean the other can be a very hard bug to track down. Be careful with those. So that's the end of our tour of integer types, their operators, and their representations. But that's not the end of numeric types. In this lecture, we've seen integer types in C and sort of logical types. But there's a world out there beyond integers, and that's up next. Again, we begin with an unbounded mathematical concept that doesn't really work in the finite confines of a physical digital machine. And so again, the fields of computer science and computer engineering must design to get as close as possible to the mathematical ideal within these constraints. In this case, the concept is floating point numbers. Floating point numbers draw on the idea that by breaking down very large or very small numbers into expressions that fit a given pattern, we can use most of our information on details that change, not the pieces in the pattern that are the same. In this case, it's a multiplier times the exponentiated common base. The powers are inherently reasonably small because of the fast growth of exponentiation, and the base is constant. So we're left with the majority of our data to store the multiplier, which is the most variable portion. We started here with the integer types. We might as well do the parallel take on floating point types. C provides 3 of these: float, double, and long double. The sizes, like with integers, are unspecified, but constrained into an order. Floating point literals have a decimal point, an E, or both. By default, they're doubles, but they can be suffixed with L to make them long double or F to make them floats. So reflecting again on the design decisions here, I think that the double type provides the range of precision required for most applications, so that makes sense. It makes sense that double should be the default floating point value. It also fits with int as the default integer value in that there's a middle ground for the default and we can go higher or lower, larger or smaller. Interestingly though, for floats there is a suffix defined for the shorter version of the literal, unlike with integers, with shorts. The names are a bit wonky too because there's a historical artifact more so than anything else. At the very least, they could have been consistent with the integer types and been short float, float, and long float. Or better still, again, what we talked about with integers, something like float 32, float 64, and float 96. But either way, C++ and then Java inherited these same eccentric type names, so it seems we're stuck with them whether we like them or not. So now let's look at the representation of floating point numbers in greater detail than just a fuzzy sense that we need to keep a mantissa and an exponent. In 1976, Intel began planning to produce a floating point coprocessor, and William Kahan, who would eventually win the '89 Turing Award for his contributions to numerical analysis and digital representations, was the lead consultant. A draft standard was put forth in 1977. The 1980 processor 8087 was the first chip to implement it, and the standard was officially adopted by 1985. So the IEEE standard is basically the only way of representing floating point in modern systems. There's 1 bit for the sign, a third or less of the bits constitute the exponent, and the rest go towards a binary fraction that sums to the mantissa. So IEEE 754 standardized it, but really the concept isn't new. The term itself is over 100 years older than IEEE 754, and the idea of keeping a variable amount of precision, depending on the values, dates to way before that even. Here's a concrete example of the bits in the representation of a floating point number, in this case a float. Fear not, we won't ask you to compute this, but we can just see here that we've got 1 bit set aside for the sign, where 1 here means it's negative. There's 8 bits for the exponent, which is relative to 127. We have 23 bits for the mantissa, which is just a sum of exponents, so sort of a binary fraction in that sense. And when we put it all together, we can get to a final representation. So a few things to note here. Because these are all just numeric approximations of real numbers, there are some different rules to play by that we can't just make assumptions about exactness. You probably learned in 126 not to compare floating point numbers for equality because you could end up asking if something like 0.999998 is equal to 1.00002 when those two numbers might well have been the result of computations that should algebraically be equivalent. The proper way to do this is with various expressions using the minimum value differentiating 1.0 from another floating point number called the machine epsilon. But the details, though, are beyond the scope of this course because the difference between x and the next floating point value above x varies according to x. So the machine epsilon is specific to the number 1. It doesn't work for differentiating between 0 and the next floating point number above 0, for instance. There are some decent approximations about these approximations, however, and so you can use the rules of thumb on the slide if you want to get a general sense of how precise the float or the double is. So really the strong takeaway you need to know beyond the available types in the language and a vague sense of how they're represented are these implications of how they're represented. As noted before, equality comparisons are fraught, and additionally you might have learned in 126 there's potential for catastrophic cancellation and similar issues where one or more operations substantially increase the relative error in the approximations. And so the calculation can be wildly inaccurate due to only the compounding of small errors. In real systems, oftentimes it's worth using scaled integers instead of floating point numbers when possible. So, what does the following code print? Take a moment, see what you can come up with. So this is actually hard to say because we have two different things going on that unless you actually try it out or unless you know very deeply the standard, you can't really predict. We have a loop that's checking for equality, or rather inequality, with 10.0, and then we have a sum checking for equality with 1.0. As it ends up, the loop does terminate because we can represent 10.0 exactly by adding 1.0 at a time. But sum isn't 1.0 because we can't represent 1.0 exactly by adding 0.1 at a time. Again, these are details that you don't need to know the specifics of, but these are considerations that you should know about and be able to at least discuss in terms of what you need to consider. All right, so in summary from this lecture, which I apologize is a bit long, we've seen integer types in C, we've seen their representations, both signed and unsigned, we've seen logical types in C for whatever that's worth, and then floating point types in C and their representations. This wraps up the second crash course lecture. Next time, something new and different. Pointers.